Alright, good morning folks. Going to start today with a talk by Sabrina Hao from the University of Pittsburgh. So thank you very much. The floor is yours.
Thank you. Thank you very much for being here. So today we're going to talk about particles. So my project started with an observation when I studied quantum mechanics from the physics department and at the same time studied philosophy of quantum mechanics in the philosophy department. And I realized that, so on one hand, in philosophical discourse, we have all these amazing ontological theories like wave function realism, Bohmian particles based on Bohmian mechanics, and mass density ontology and flash ontology based on JRW theory, and all other theories that I'm not listing here. And on the other hand, in the physics department, scientists keep talking about particles, right? There are different kinds of particles, for example, fermions and bosons, and there are electrons, protons, and they make up atoms. And in EM theory, we have the EM fields, and also if we go to quantum field theory, we have all kinds of quantum fields. So it makes me wonder, so on this side, right, these ontological theories, they publish a lot of papers, I know the arguments for and against them, I know what they are. But on the other hand, I'm confused or curious what scientists are talking about, right? What exactly are particles? So among these ontologies that they are talking about in their linguistic behavior, I'm going to focus on particles here, and therefore I'm going to focus on non-relativistic quantum mechanics for this talk. Quantum field theory is amazing, but it's so much more complicated, so we don't have time for that. So here's a question that I'm asking in this talk. What are scientists talking about when they talk about particles? And this question can be unfolded into two questions. One is we can ask, what are they talking about in scientific practice? So that's just a philosophy of scientific practice. We can just ask, what do they mean by particles in their context? But another question that's more interesting, I think, is for ontological theories. So for example, if you're a wave function realist, we can still ask you, what are scientists talking about when they talk about particles, right? Because you think what there is the wave function. Then what are scientists talking about then? So to motivate a little bit more why this question is interesting, I'm going to draw a parallel case from the debate about scientific realism. So this is Frank Crossan's famous book, Scientific Image, and this is in the first chapter. So right after he introduced scientific realism and anti-realism, he immediately asked this question, what does a scientist do then, according to these different positions? And he thinks that no matter so if you're a realist, then the question is easy, right? The scientists are trying to find out what is true about this world. But if you're an anti-realist, there's a story that you need to tell. You need to explain scientists' behaviors. So but Crossan didn't argue for why we need to ask this question. So I'm going to just make an analogy and think that for this context that we're talking about, I think that our ontological theories also need to explain scientists' behaviors, including their linguistic behaviors when they talk about particles. And so this is my first attempt. So one question you might want to ask is, what about the measurement problem? So scientists are notorious about making claims like collapse upon measurement, measurement causes collapse. Those are just basically nonsense BS. So if scientists are talking about nonsense, then why do we need to even explain their behavior? So one might have this kind, so nobody has like formally argued for that, but I feel like some philosophers of physics have this kind of feeling in their mind. So I want to draw your attention to David Wallace has a paper in 2016 called What is Orthodox Quantum Mechanics? There he argued that actually the postulate of collapse upon measurement, which he divides into the E link and the collapse law, are actually do not play any role in actual scientific practice. So scientists might talk about it for convention or for communication, pragmatic purposes, but it doesn't really play a central role in scientific practice. In other words, if you drop those postulates, the scientific results we have, the scientific success we have is not going to change. So my revised argument is our ontological theories need to account for scientists' behaviors, including linguistic behaviors, which play a central role in scientific practice. Because these behaviors lead to scientific success that we appreciate. And the particles talks do play, I want to say that the particle talks do play a central role in scientific practice. I'm not making a counterfactual claim or a necessity claim that if in another possible world scientists use some other language that they won't reach the success that they have right now. I'm not making that model claim, but I'm just saying that for what we have right now, all the research papers we have, if we drop all the particle terms and particle talks, they will not be able to communicate, they will not be able to reach the scientific success they have right now. So that's what I'm arguing. Okay, so now I think both questions are efficiently motivated, so now let's think about the answers. The first one is, what are scientists talking about when they talk about particles in scientific practice? So my methodology is I looked through a lot of research papers on Physics Review, on other Nature, other journals, and also I looked through a lot of, maybe not a lot, like 5 to 8 textbooks on quantum mechanics. And this is my summary of what they think particles are in non-relativistic quantum mechanics. So obviously, particles are what we study, at least part of what we study in particle physics. Hence the name particle physics, we better study particles. Particles are what we study in non-relativistic quantum mechanics, besides EM field. There's no other ontologies that seem to be postulated. And particles have properties such as momentum, position, spin, mass, and charge. And this might be an interesting one. I think, so this kind of expression are more explicit in textbooks. So I found in textbooks that there are explicit expressions that says that wave function are representing the position properties or momentum properties of particles. You don't find that kind of explicit expression in research paper that much, but I think, although this is my interpretation of what scientists are talking about, but the way of wording, for example, they're saying the mass of the particles, the charge of the particles, they're using it as the same way when they say the wave function of the particles represent the position or something like that. And also, although wave function is doing a representational role in scientific practice, but I don't think that they're doing a representational role as in they're postulating wave function as an entity, because when they say that the wave function is representing the position of the particles, they would say that, so where is the particle? Then the particle's position at that point is undetermined, or even asking the question where the particles is meaningless. Because the position is just represented by the wave function. Maybe we can talk about that, more about that in the Q&A. And of course, particles can have the property of can be entangled with each other. And this is in quantum field theory, they are excitational fields. So even for scientists, particles are not the fundamental ontology. So no matter how you interpret what they mean by excitations of fields, what you get from it at least is that particles are emergent ontologies supervening on fields. So that's what I gather from a research paper, what they mean by particles in scientific practice. So let's think about the other question, what are particles for ontological theories? So I think you have two options. One is you can be realist about particles. So you think that particles exist, there are such entities as particles, and those entities are what scientists are referring to. And of course, particles do not need to be the only ontology or the fundamental ontology. It could be emergent on something else. And one example I can think about that adopt this position is this field interpretation of quantum field theory. You can argue, based on the field interpretation, you can argue particles as the emergent ontology supervening on field. Not all people adopting field interpretation adopt that, but I think David Wallace has a paper arguing for that. So you can, another curious case that I was thinking about is if you are a structural realist, if you think the structure is the more fundamental ontology, maybe you can recover particles as emergent ontologies from the structure. But I haven't looked into that yet. On the other hand, you can be anti-realist about particles. So you would think that particles do not exist. But then the question becomes, so, well, what are scientists talking about, right? There's no particles that they're referring to. So we need to explain scientists' language about particles. So here we have two options. One is that we can think that scientists' language about particles is not literally construed, and they gain meaning through connection to other ontologies that whatever you prefer. And maybe you could think that the connection could be the mathematical formalism. So maybe you see an analogy to the debate about realism and anti-realism. This is how Van Fraassen categorized the anti-realism position as well. This is analogous to the logical positivist view, which they think that the theoretical terms gain meaning through connection to the observational terms. But although there's an analogy going on, but the failure of the positivist program has nothing to do with this program here, because we're all committed to some kind of scientific realism here. Because no matter what ontology you propose, you think that our theory, quantum mechanics, tell us something about what there is in this world. So that could be one option. Another option is that you think that scientists' language about particles is literally construed, but it's just not true. And you might also, so this is back to the analogy of the realism and anti-realism debate. That's where the constructive empiricist goes, right? They think that you need to literally understand scientists' language, but they're just not true, but they're empirically adequate. But again, you will see that this analogy later. So here's the map, what options you have if you're proposing any kind of ontology for non-relativistic quantum mechanics. You can be a realist, you can be anti-realist, and then you can think that the particle language is not literally construed or not true. And here comes my second argument, is that I think the last option, which is this option, cannot be motivated for all positive ontological theories. What I mean by positive ontological theories is that first you commit to some version of scientific realism. You need to think that the theory of quantum mechanics telling us something true about what there is in this world. And you're also committing to an exclusive ontological interpretation of non-relativistic quantum mechanics. Say if you are wave function realism, then you think that this is the true way to understand quantum mechanics. This is what quantum mechanics tell us, that there's wave function in this world, but not particles. So let's think about any ontological theory want to adopt the third option here, that scientists' language need to be literally construed, but they're just not true. So this is just from a research paper. It doesn't, the content really doesn't matter. What I'm focusing on is just this sentence right here. So we have some kind of formalism that we should all agree to, that even any revisionary ontological theories need to agree that this tells us something true about our world, right? Because you're committing to some kind of scientific realism. So this is scientist interpretation, right? ME is the electron mass. And if you're adopting the third option that I was talking about, then you think that this is just not true. This is just false, right? ME is not the electron mass because there's no such thing as the electron, right? They will probably think that it's something else. Wave function realism might think that this is some parameters in the wave function or something like that. But the problem is, so maybe you want to say that that sentence is not true, but it's empirically adequate. So you're going the constructive empiricist route. But on the other hand, this analogy between this position to Van Frassen's position is that you're thinking some alternative ontology to be the true one, right? Van Frassen's constructive empiricism says that, okay, scientific theory is not true but empirically adequate. On the other hand, he doesn't say anything alternative that is true, right? We're just saying that we don't know whether our scientific theory is true or not. I'm not postulating anything that is true. So, but here, the ontological theories, here, adopting the third option I was talking about, you're saying that particle charge is not true but empirically adequate, but the ontology that you propose is just empirically adequate as well. Sorry, are both empirically adequate. That's a typo. So we have a problem of underdetermination. And I think that so there's been some discussions about underdetermination of ontologies of quantum theories recently as well. For example, the flash ontology and the mass density ontology both are based on GRW theory, but they are both empirically adequate or empirically equivalent to each other. So there's that kind of underdetermination as well. But I want to say that what we're talking about here is slightly different from that. The first is, of course, what I've been trying to convince you is that the virtues of the particle talks is that it leads to scientific success. Right? Scientists are believing them, are using them all the time, communicating through the particle language, and it leads to all the scientific results and success we have right now. So there's that virtue. On the other hand, if we think about this logical route when we learn physics, right? We learn physics from physicists, right? Probably every philosopher and physicist learn quantum mechanics through the particle language, right? Because you just cannot skip it. You learn electron, what is electron, you learn how to construct a wave function for a one-dimensional electron, for two-dimensional electron, for three-dimensional electron, and then two electrons, how they entangle. So if you think about this, then you first learn physics from the particle language, and then you need to actively deny that and say, no, that's actually false. And actually, the ontology that I'm proposing is the right one. So there's an active denial going on that doesn't exist in other underdetermination cases. And so maybe let's think about the active denial. So maybe we can argue that particle is just not a coherent concept. It's just like the collapse upon measurement. It's just nonsense. So we don't need to. So we have enough reason to deny it. So I'm going to gather some conceptual problems that have been raised against the particle concept in the philosophical discussions and see if they actually do the work to deny the particle concept. First one is non-separability. So we know that particles can be entangled with each other. So when they're entangled, their state-dependent properties, their position, their momentum, their spin properties cannot be represented without representing the whole the properties of the whole system, right? So their state-dependent properties are can be non-separable. But on the other hand, particles have state-independent properties as well. So some philosophers might think that the non-separability of particles kind of deny the individuality of particles, so we cannot see particles as an individual entity anymore. But I want to argue that, well, particles have state-independent properties as well, right? You have massive charge, spin, which means electrons is spin half. I'm not saying that you're spin up or spin down. I'm saying the spin property as the spin half, spin one, spinless. That property is actually state-independent, right? It tags with it sticks with the particle all the time. So if we can specify some properties that can individuate each individual particles, then I think its individuality is not threatened simply by non-separability. And also, on the other hand, in experiments, we kind of require our particles to be separable from, at least from the environment, right? Because if our particles are not separable from the environment the whole time, we won't even have interference results because the coherence will just kicks in all the time. So, for example, if we're doing an interference experiment, we need to at least assume, right? We need to manipulate our experiments so that the particles in the experiments, the objects of the experiments, are separable from the environment. So, in some sense, and plus the coherence, in some sense, particles can be separable and can be non-separable from other particles or from the environment. So I don't think that's a decisive argument to argue that particle cannot be individual object. So another one is indistinguishability. So identical particles, they share the same mass, charge, and spin. They share all the same state-independent properties, and they just cannot be distinguished from each other. So I guess here I just need to bite the bullet because scientists do seem to suggest that identical particles only possess numerical identities. So some philosophers, especially the principle of indiscernible identity from Leibniz, they use that principle to argue that because particles only have numerical identity, they lose the metaphysical sense of individuality. So here I'm just going to bite the bullet. I think that we can just reject our metaphysical principle based on our scientific findings. So I don't think that's a decisive argument against the particle concept. Another one is someone like Maudlin might think that particles, as how I represented just now, is not the local variables. Well, it's fine because particles do not need to be the only ontology in your theory. So it's not local variables. It doesn't say that particle is not a coherent concept. Then if you want local variables in your theory, you just propose something else. And the last one is the measurement problem. So one might think, because scientists do not propose any solutions or decide on any solutions to the measurement problem, you might think that, well, the solution I think is right, for example, Bohmian mechanics, is just incompatible with the particle concept. Then, do you get a free escape route to say that, okay, then I can just deny the particle concept? I think not. I think the question just push one step forward to the solution to the measurement problem that you adopt, and now it's the question for Bohmian mechanics that you need to explain scientist language, right? It's the same. So if you think that Bohmian particles are derived from Bohmian mechanics, and Bohmian mechanics are incompatible with the particle concept, then the question becomes directing to Bohmian mechanics and what are scientists talking about then. So if there's no active denial arguments that can thoroughly deny particle concept as a coherent concept, then I would want to argue that this is actually the only available positions for any ontological theories. You either be a realist or be an anti-realist and think that the particle terms gain meaning through connection to the ontology that you propose. 5 minutes. Okay. Which position actually is more fitting for one ontological theory? Actually, it depends on case by case. So, because of the time limit, I'm going to study wave function realism only. But I've thought about Bohmian particles and the GRW primitive ontologies as well. So if you are curious, I can answer them in Q&A. So let's think about wave function realism. So wave function realism thinks that what there is actually this high-dimensional entity that's represented by the wave function. So can wave function realism establish particles as emergent ontologies? I think not. So in the existing literature, so Albert and Ney, so they're actually responding to a different question, right? They were responding to the macro object problem because there's this challenge for wave function realism that they can't recover the three-dimensional world that we are experiencing every day. So in their books, they actually managed to recover three-dimensional micro-objects from the wave function. I'm not going to go into details of that, but I'm just going to point out that the resulting micro-objects that they recover from the wave function is not particles. They're three-dimensional micro-objects localized roughly where particles are. But so they only recover the position property of particles, but that blob or the sub-region of the wave function, it's not particles because they do not possess the state-independent properties. They do not possess the mass, the charge, other properties of the particles, right? And it's hard to say that those blobs can be entangled with each other. And another problem is that wave function is basically a field, right? If you take that as the entity, then your ontology is a field ontology. But that's very different from what scientists have in mind about particles, right? Particles are what they are postulating right now is that particles are still point-sized, right? Although their position is not definite most of the time. So, okay, so that's not a good option for wave function realism. So maybe we can think about maybe the particle talk can gain meaning through connection to the wave function. So I think that's a better option for wave function realism. So when scientists are talking about the state-dependent properties, the momentum, position properties, so they're actually talking about the configurations of the wave function. And when scientists are talking about the state-independent properties like the mass and charge, the wave function realists can say that they're actually talking about the parameters in the wave function. So I think that's a better strategy for wave function realism. Although we've been only talking about spinless particles. And all the discussions about wave function realism at this point, I think, are mostly for spinless particles. So more work needs to be done, but let's just think one step forward for them and think about what if we add spin to the particles? I think it's going to cause a problem for wave function realism because a particle being, for example, being spin half, you kind of have two copies of the original wave function into a Hilbert space, right? So how does the sentence that electron is spin half can gain meaning through the wave function? The best we can do is to say that maybe they're saying something about the wave function takes value in the Hilbert's, the dimension of the Hilbert space, it's ×2, or duplicates the dimension, if that makes sense. Because think about, we're talking about one particle is spin half, right? So let's think about this, for example, this is the wave function of, actually, Right, so this is the wave function of everything else and including all the spin. So this could be already a Hilbert space vector already. And when we say that one particle is spin half, so we are duplicating the whole thing into 2 copies. So I think it's going to be awkward for wave function realism if we add spin. So all right, time is up, and that's it. Thank you very much.
Now we have a comment from Chanwoo Lee.
Yes. It's maximum 10 minutes, right?
Yes, absolutely.
Yeah. I'll probably, should I go, like what's like?
I'll do some welcome to
I'll probably just.
or maybe there's a camera.
Oh, okay. Alright, thank you. First, thanks Sabrina for this presentation. And first, let me give a brief recap on my understanding of the paper and the presentation again. So what's being proposed in the paper in this project is that philosopher of scientists, philosopher of science, philosopher of physical sciences should pay attention to the scientific practice, even when the ontology of particles are concerned. So, for example, scientists, like physicists themselves, talk about particles all the time, thereby, to use philosophical jargon, gradify them. So, whenever we philosophers are being revisionary about them, then that carries a burden. For that reason, so the first argument given by Sabrina was that philosophers, whenever they're trying to give an account of the ontology of particles, then yeah, you should be able to recover this. And there are many revisionary possible approaches, and one possible approach is that yeah, you kind of be fictionalist about it. I don't know if this is the right way of putting it, but you are saying they are not literally true. And in that case, it was argued that this is probably not a good idea. And this was kind of also considered in conjunction with the recent form of wave function realism. So this is was my understanding of the presentation. And first, I'm very sympathetic to the general proposal. So I first happen to be interested in both the ontology of particles issues, and independently, I happen to be interested in the scientific practice approach in philosophy of science. And for some reason, I never really combined together. It's such a great. I was like when I first saw the after, I was like, aha, yeah, this had to come out. So it was so timely, and I thought. So perhaps it was just my ignorance, but it was my first time actually seeing this explicit kind of proposal. So I was very, very excited about it, and I think this is a very good attempt, and I love to see even more of this. So yeah, I'm very sympathetic to your proposal. So. And yeah, so I had several comments, and I don't want to just talk about them for a long time because I don't want to take too much time, and I've also conveyed my comments to Sabrina earlier. So I just want to propose one question which might be useful for Q&A. So I think this project is by and large negative, saying, hey, revisionary ontologist, you come up with this philosophy, but it does not seem like you were doing a very great job of recovering particles. At least you need to be aware of it. I think that's a really good point, and I think Sabrina is doing giving us really good arguments here. But at the same time, I was wondering, what could be the positive picture here? So, what does a literal reading of non-relativist quantum mechanics tell us about the ontology of particles? So, of course, this is not something that has to be given at the moment because this is more of a negative project. But I was still wondering, at least in this dialectic, I just wonder whether if the presence of a positive ontology might make a difference. For example, I think here regarding I think it was a second argument where the underdetermination issue arose. And so the argument went, okay, so there is when this comes to particle ontology versus the alternative ontologies, well, like maybe we don't like it, so we want to perhaps prefer the more literal understanding, which leads us to the literal ontology of particles as well. But it seemed, at least from the paper, if I understand right, it seemed wasn't. I think like still the positive literal ontology of particles is something that needs to be worked out in more detail. So as an analogy, so yeah, I personally work more on philosophy of math, so let's take just mathematics. Like when it comes to mathematics, I think the literal ontology should be something like very full-blown Platonic kind of realism kind of stuff. Like, yeah, numbers do exist, they're abstracta, they're heavenly relevant, and so on. And yes, people don't like it for obvious reasons, but there is that kind of stuff. And I just wonder, it was personally my ignorance too, so that leads to some kind of working realism in mathematics. So just take mathematician's word, and just that gives us this. And I just wondered what the quantum mechanics counterpart could be in the when it comes to quantum when it comes to the ontology of quantum particles. So of course, like it need not be done here, right here for this project, but I just like wondered what that possibly could lead us to. So I think this may dialectically matter, because otherwise, like if the account has not been worked out yet, then I think the proponents of the alternative ontologies might say, yes, we have this shortcomings. Yeah, we are being non-literal, so this is not the best, but still, before we have the literal ontology, maybe we are still kind of more viable competitors at the moment. So therefore, yeah, alternative ontologies should be taken seriously, or so they may argue. So yeah, so this was kind of the main question I had about, and like I just liked to hear from Sabrina more about it. Thank you very much. That was a good time.
Right. I think I have 2 points. So one is that so we can't just get the ontology from scientists, right? Because I was actually thinking about, so when I started the project, I was actually thinking about what's the methodology I should do to understand what they're talking about when they talk about particles. And one thing that I rule out is to have a survey or a face-to-face question kind of methods, because we are philosophers, right? Once we start asking philosophical questions, scientists get confused as well. And then I have a colleague actually try. If you try to talk to science, introduce wave function realism to physicists, they're like, oh sure, yeah, wave function, why not? So that's why I use the methodology to just look at research papers, because that's the pre-philosophical belief, the pre-philosophical, unpolluted scientific language, right? So yes, so the positive account, if we want to develop when we're on our own, we can't just squeeze it out from scientists. And to develop a positive account, the main concern is the measurement problem again, because scientists do not. So I think there are 2 ways, right? One is that you think that scientists did not decide on the measurement problem, so what they're doing is compatible with all the realist solutions, or even non-realist solutions to the measurement problem. And another one is that you might think that maybe Everettians would want to claim that. I think that Wallace is very sympathetic to it, but if you think that maybe they are implicitly adopting one solution, that is the Everettian, because Everettian or all the solutions that do not alternate the formalism. Because if you think that the scientists are using this formalism, which means that they're probably not having Bohmian mechanics in mind, and probably not having GRW in mind. They probably have some kind of Everettian many world theory in mind, because that solution does not alternate the formalism. So yeah, I think that there's a lot of work to be done to develop a positive account. Especially, you need to develop that based on a solution to the measurement problem. You can't kind of just escape that and directly talk about the ontology of quantum mechanics. So that might be one problem, that you are you are in some anyways deviating from the language in scientific practice. But maybe if you're adopting Everettian, you're best off. You can recover probably all the languages in scientific practice. That would be my guess. I haven't worked it out. So that's my. Thank you very much.
All right, any questions? Yes, please. And Sebastian.
Oh, okay. Cool. So from what I gather, you follow David Wallace's assertion that scientists should drop the end-state eigenvalue line. And if they do, nothing will meaningfully change about their practice. But I wonder about how we go about the business of ascribing state-dependent properties to the objects that scientists call particles without the EE link. State-dependent properties, like this particle is spin operator.
So positions and momentum.
Yeah, position, momentum, spin, various other state-dependent properties.
Right. So in the formulas that they're represented by the wave function, right? And that's about it.
So I guess like how do we get that without that eigenstate eigenvalue link? Or perhaps what is to you? So what's disagreeable about the EE link?
I don't think I'm arguing specifically against the EE link. I'm just saying that the scientific practice doesn't need it. Yeah. So no, I think that's a good question. I didn't think too much about it. I think that. So yeah. So what I'm trying to say is that scientific practice doesn't need to have this Copenhagen interpretation, this nonsense collapse upon measurement thing to operate, to have the scientific results we have. But yes, the measurement problem is still there. And I think they don't have the EE link, but they have the Born rule. So yes, yeah. So I think I understand. So if they're not postulating collapse, then they're basically lacking a solution to the measurement problem, right? If you supplement Everettian there, then the branching will help. Even without the EE link, but just with the Born rule and the branching, you will have the measurement results.
I think so. Yeah. We should talk more. I'm really interested.
Yeah, thanks, Sabrina. So I'm very sympathetic to going back to like scientific practice and paying attention to what scientists are saying. But I was wondering, if you do that, you also will find a lot of cases of scientists saying, oh, you can no longer make sense of particles in the standard sense in quantum mechanics. Sometimes they go even further, right? As you know, they would say, oh, there are no particles, or they would say things like the notion of particle that comes from classical physics or something completely breaks down, and things like that, right? And so, if they do also say that, in addition to also talking about what look like particles, right? It's not so clear to me that scientific practice will, like, I guess that's a problem in a way for the kind of project where you say, okay, go back to scientific practice, because scientific practice in some ways is inconsistent, right? Because they say things that sometimes even they seem to contradict themselves or things like that. But so I wonder, like, that coupled with the fact that, and I think you mentioned that about non-separability and other things, right? Like, what is the notion of particle? I guess I don't like sometimes when people say it depends on what you mean, because that's not a very good argument. But in this case, like, I guess we need to be clear about what is the notion of particle that we are assuming in the background. Because if you say it can survive non-indistinguishability, and it can also survive non-separability. And all of this, then it starts to look like a new term that is not, I guess, it's a meaning of particle that maybe we have in our mind. Does that make sense?
Yeah.
Like what is the bare bones notion of particle that survives all the things that you live there and you can still say, okay, this is like a particle. This is maybe related to the comments.
Right. So if you look at scientists' definition, the very first thing they would say to define a particle is the state-independent property, the mass, charge, and spin, whether it's a fermion or boson, that kind of thing. So that's how I find it in my research. So, I think the biggest bite is the indistinguishability, right? I think there's one or two textbooks that's very, very explicitly say that particles only have numerical identity. So like the short different kinds of particles, like one electron and one proton, a photon, they are different, but in qualitative difference. But within all the electrons, they only have numerical identity. So that's one thing that's definitely challenging the traditional metaphysical understanding of what entity is. About non-separability, so one thing that I find in scientific practice is that they're treating the wave function kind of similar to like the phase-space trajectories in classical mechanics. So they are representing the properties, and they're doing a lot of representational role, but on the other hand, it's always they start with how many particles I have, what kind of particles I have, and then they construct the wave function. So there's this reasoning process from what particles we have to what wave function we need to represent them, to represent the position of them. So I'm definitely, I think what scientists are doing is definitely different from what philosophers would think, that if the wave function is the only thing that's doing the representational role, then that's what there is, right? So maybe, just like Chanwoo said, I'm doing a very negative project here that maybe I don't have a positive account of what a particle is, but on the other hand, I also don't know what else I need to for this positive account, right? That's another thing that I need to think about. And I think there are some philosophers like I think Saunders. Who else have the weak discernibility program for the?
Does Stephen French have something? Simon Sanders, and I think Stephen French has some variations.
Well,
Yeah.
he has the notion of what he calls quasi-sets, but it's not quite the same as the thing which Simon has in terms of weak designability, which is more geared to the kind of getting the ultra-thin notion of objecthood that still leaves you with just a kind of smidgen of quine. Sorry, it's a little
Not true.
But can I ask a supplementary on that? I mean, I think the problem with the position that you've just outlined in response to that question is that, yeah, although it might work for non-relativistic quantum mechanics, certainly when you go over into quantum field theory, where of course I accept obviously the notion of particle is moot anyway in the QFT setting, but you do immediately have the additional complication that particle number becomes, the occupation, the number of particles in a given state becomes a quantum variable, and you have phenomena like Rindler quanta where you precisely can have superpositions of states of different particle number. So the very notion of numerosity, even the bare, cardinality, which of course when you say there's still some notion of individuality in terms of in terms of the number of particles in the non-relativistic QM setting. But that's only in respect of the bare cardinality. It precisely isn't the case in respect of ordinal numbers, because these things don't have an order type. There is no fact of the matter about which is the first or the second particle in the state. That's they lack a kaitas, as the medievals used to say. So at the very best, on the very best reading, from the point of view of somebody who wants to hang on to this metaphysical notion of individuality of the particles, it's bare cardinality. And for that reason, it seems to be that if you want to answer the question, what survives of our notion of a particle in scientific practice, the ontological structural realist answer is probably the most convincing, because it would be something like irreducible representations of the Poincare group, or some answer that gives that couches the answer in terms of group representations, and that level of abstraction of the structure, because clearly that does survive in the formalism, but it's quite unclear that anything which makes connection with the kind of intuitions that are at the centre of our debates about the metaphysics of individuality and non-individuality survives.
Yeah, when it gets to quantum field theory, it gets very, very complicated.
Yeah. But getting to quantum field theory is not, as it were, an optional extra.
Yeah.
Because I'm afraid that is the way physics is. I mean, quantum field theory is at the moment our best developed, best underpinning for non-relativistic quantum mechanics. So I mean, you couldn't, surely for methodological reasons, expect to go to non-relativistic quantum mechanics for your stab at the ultimate ontology, or even the working ontology, the working physicist, which is where I think that your point with the analogy with the situation in philosophy of mathematics is actually very instructive, very helpful, except that I'd actually take almost the opposite moral from it, the one you drew, because if I understood, you were saying you thought that you're broadly speaking a Platonist about mathematical structures, and you think that mathematical practice actually underpins that position. Is what I'm saying. I would say mathematical practice actually underpins a radically sort of anti-ontological position, that there is no ontology here, speaking in mathematics. So what there is are intersecting patterns of occurrence of structure within further structures, with no obvious bottom level, and in fact the very notion of kind of top or bottom level is in a sense meaningless, because as the Zusammenhang of mathematics, or our mathematical practices, evolves, we'll have different patterns of explanation, different patterns of what viewed ontologically might be candidates for grounding in some sense, but no clear indication of how those make connection with any proposed ultimate ontology. And it seems to me we're in a very similar position in physics.
Do you want to repeat that? Or otherwise we are...
I'm sorry, that was very long-winded. It was more a comment than a question. My apologies.
I wanted to say something, but I forgot.
Right. Let's move to Sam's question.
A couple of big picture methodological points. So you're talking about a domain of discourse, like talk, scientific talk, and you're running an analogy to like the anti-realist debate in philosophy of science, but it's not obvious to me that that's directly analogous to what we're talking about, because that's about theories, roughly speaking. So for instance, when you talk about talk being empirically adequate, it's not clear to me what that means, because empirical adequacy, at least in the Van Fraassen stuff, is about theories, not about domains of discourse. And a more sort of direct analogy looks like the debate about moral discourse, where a lot of the options that you're looking at are sort of options in the case of moral thought and talk that people run. But if you look over there, there are more options than the options that you considered, right? So you've got also the idea that the talk is not truth act, that it's not even like expressing propositions. So that some people think that moral talk is just like expressions of disgust or pleasure and things like that. So like there are just other options once you look at sort of other work in philosophy that's looking at domains of discourse, and so I think it might be worth taking a look at those sorts of cases. I had another thought, but maybe that's enough for now.
Yeah, no, that's helpful. Yeah, I haven't looked into that, so I'll take a look.
Yeah.
You can continue
I'm not sure I can remember the other thing I was going to say. So.
Oh, I remember what I wanted to say.
Sure.
Yeah, so I haven't figured out my what I try to argue for in the QFT case, but I think so. If we find out that there's no way to maintain or survive this particle concept, then I maybe look the other way, and my question would be then why are scientists still talking about it all the time, and why are these talks are still leading to so many successful communication and successful scientific findings? So that would be the next step I would take a look, which, yeah.
Sure. And that would be a very good
right?
question, I agree. That would be
Yeah,
a very good question, because clearly it has been historically a very successful concept.
Yes.
But that's equally true of many concepts which we regard as emergent, as not, as no longer candidates for or giving us our, as it were, our best, heuristic window onto candidates for the ultimate ontology.
Yeah, I remember what I was going to say. In the moral case, you also have a distinction between descriptive and prescriptive readings of discourses, right? So are you describing what moral talk is in fact about, or are you saying what it ought to be about? And actually a lot of the work in the moral case is on the prescriptive side. Yours seems to be on the descriptive side, right? Like what is scientists in fact talking about? But then some of the stuff about the positive view might be more on the prescriptive side. And so I think it's worth thinking about exactly whether the project is descriptive or prescriptive and how those two things interact when you're thinking about scientific talk.
Yeah, I think so I want to keep the descriptive side, and because I don't want to propose, at least in this project, I don't want to propose scientists ontological interpretation as the competitor to all the ontological theories that we have proposed, right? I want to do a descriptive account of what they're talking about, and I just want to argue that no matter what ontological theory you have this burden to explain what they're talking about. But yes, if I in another project propose a positive account, then it becomes a competitor to other accounts. Then I need to think about arguments for why we need to adopt this account and why the other accounts don't have the virtues, or we should abandon the other ontological commitments but adopt this one. Yeah, that would be a very different project, I would think.
Yeah, I mean, one reason to be prescriptive here relates to some of the things that Sebastian was saying, which is that it's not obvious that the scientists are going to be consistent in how they talk, right? I think we assume that scientists have a unified way of speaking about things, but actually it's all over the place for everyone, right? And so the prescriptive side of things is to bring some order to the scientific discourse for their own good, I think. So that's a reason in that direction.
All right, so we stop here. So thanks a lot again for